Welcome everybody, welcome to this course. This course is a little bit different from what we have on Codeforces, so I think most of you come from Codeforces side, and we have algorithms course in Codeforces. The course on Codeforces is basically dedicated to competitive programming, so we talk about some practical algorithms and some tricks you can use in contests. And this course is very different, so in this course we will talk about fundamental stuff. So it's mirror of my ITMO course about algorithms and data structures. So we will talk about some theoretical aspects of algorithms and data structures, discuss some different fundamental algorithms and so on. The course is very long, so this course is 4 semesters, so we have 2 years of lectures. So I'm not sure if everyone is ready for this, but we'll see. We'll have streams probably every Friday at this time. Maybe I'll change it. I'll have another post on Codeforces if I change anything. And you can look up for a Google Calendar in the bottom. So there is an actual calendar of my lectures, so you can just adjust your schedule. Okay. I'm not sure about practice, so I plan to have some practice tasks, but not like, maybe we'll have some contests, like when you need to program some algorithms. And maybe we'll have some theoretical problems. So maybe I will post some theoretical problems, and then you submit your solutions, and then I will read these solutions and discuss them on some different stream. I'm not sure yet, but we'll see. We'll see how it will go. Okay, so everybody here, yeah? Everybody ready? Go. So, today is the first lecture. We will talk about very basic stuff. We will talk about what is an algorithm and how to measure its efficiency. So, what is an algorithm? I don't like this marker. Sorry, technical difficulties. I'll find another marker. Once again. We'll start with very simple things. We'll test what is an algorithm, how to measure its efficiency. So what is an algorithm? Algorithm is basically some formalized way to solve some problem. So you have some problem and you need to formalize the solution of this problem. So you split the solution into some elementary steps, and so the solution is just the set of simple operations. It's very wide use term, so it is used in various different disciplines. So in this course we will mostly talk about like data processing algorithm. So in most cases the algorithm will work like this. So you have some input data, that is loaded by your algorithm, and it processes that somehow and produces some output data. And again, if you are familiar then with Codeforces side, then it's basically how most of the Codeforces problems work. So in Codeforces problem, you load some data, do something, and produce some result. So that's how most of the algorithms in this course will work. Good. For example, let's see something simple. So, for example, if we have the problem like calculate the sum of the numbers in the array. Let's see. So you have input data is some array of integers. Let's say so. Let's write like this. So you need to read this data and calculate the sum of all elements. Cool. So to produce this sum from this array, we need some algorithm. So let's just write this algorithm. To write an algorithm, we will use some pseudocode. So we will not use any real code in any real language, because all real languages are different, and it's all them some have different good things, different bad things. So instead of using some real language, we will use some pseudo language. Let's say, for example, here we can write something like, so we need some variable s to calculate the sum. Then we need to iterate over all elements of the array. Let's use for cycle, like in most of languages, for I from 0 to n minus 1. And just add this number to this s. So s plus equal ai. And in the end, we need to output, so let's print this. This language is more like Python, but not exactly Python. For example, this for cycle is not written like in Python, because I personally prefer this way. So I think this is more clear to understand than the Python way to express the cycles. So this is algorithm which calculates the sum of all elements of the array. I will upload this lecture on YouTube after the lecture, so it will be available on my site, on my channel on YouTube. So its link is again down below. Okay, let's go. So we have this algorithm. How to see if the algorithm is good or bad? So some algorithms are better than other algorithms. So to see if algorithm is good or bad, one of the main characteristics is the time complexity. So it's basically the time spent by your algorithm. Again, time complexity is basically the time that your algorithm spent to solve the problem. Please don't spam in the chat. We need some moderators in the chat, I think. Okay, now, how to measure the time complexity? Time complexity is the time spent by your algorithm. Is the time spent by your algorithm. So, in physics, for example, time is measured in seconds. Yes? Why can't we measure time in seconds when we talk about algorithms? Why can't they say that this algorithm spends like 5 seconds and so on? Why can't they do it? Any guesses? Just print in the chat. This chat is especially for your questions and for answers to my questions. So, why don't we usually measure the time complexity in seconds? Yes, oh, good, it's some feedback. Nice. So, we don't measure time complexity in seconds because all the computers have different efficiency. So, for example, different processors have different speed. So if we want to calculate time complexity in seconds, we need to fix the processor we're working with. And it's complicated because real processors, even if you fix the real processor, like let's measure time complexity on some, I don't know, Intel Core i7 processor, like this exactly processor. It will be different. It will be difficult to calculate the time complexity because it depends on very different details of your hardware and environment and stuff. So it is different to measure time complexity for a real processor. So instead of measuring time complexity in seconds for a real processor, we will measure the number of operations. time complexity is number of operations. Number of equal operations. Again, if you want to measure number of operations, you need to fix the set of operations. Like what operations are here? I don't know. Maybe this one operation, maybe it's 10 operations, maybe not. So to measure number of operations, you need to fix the environment you're working with. So this environment is called a computational model. So computational model, it is a mathematical abstraction that you use to calculate the time complexity. And not only time complexity, but memory complexity and so on. So you analyze your algorithm using some computational model. It's a mathematical model that works kind of like a real processor, but not exactly, like a very simplified version of the processor. And there are different computational models, and we will discuss different models during this course. A very basic computational model, which is like the most common one, is called the RAM model. So it's RAM machine or RAM model. Let's see, RAM model. RAM model is basically the model which simulates the usual processor you have in your computer. So it's somehow the simplified version of the regular processor. So how it works? You have some memory. Now let's ask here. Does anyone know what is RAM stands for? So these letters R, I, M. What are these stands for? Random access memory. Good. So stand for random access memory. What does it mean? It means that you have memory and you can access any cell of that memory in constant time. So let's see. If this is our memory, so this is memory. We will think about memory like one big array. So we have one big array. It's split in some cells. So each cell has some address. So this address is from 0, let's say, to m minus 1. Like m is the total memory. So in one operation, you can get any element from your memory. So you can, by this number I, you can go to memory and take this value from the memory. And you can put value in the memory. So in one operation, you can take any element from the memory or put any element to the memory. So this costs one operation. And this is the most fundamental stuff about RAM memory. Not all computational models have these operations to the memory. So in some different models, you may not have access to any element in constant time. But in this model you have. Now, besides this memory operations, you have some regular operations. Like you have all the, let's say, arithmetic operations, you have cycles, ifs, and so on. So all usual operations you have in your programming languages. We will not specify that exactly, but it's kind of intuitive. So if you are good enough, so actually, if you are to be very precise, when you specify the model, you need to specify all the types of operations you can use in your program. But in RAM model, you just can use any operations you have in any like regular programming language. So we'll not specify this exactly, but we will just think about like a usual program you have in your favorite programming language. I don't know what's buffering. If it is buffering, maybe the video quality is too big. I'm not sure how Twitch works. Not sure about this. My channel seems good, so if it's buffering, it's something on your side, I think. Good. Now, we have this computational model. Let's go back to this algorithm and calculate its time complexity. So, time complexity, again, it's the number of operations your algorithm spent to solve the problem. This number of operations depend on the input. Yeah? So if this array is big, then the time will be bigger. So when you increase the size of the array, the time will be increased as well. So time your algorithm spent is some function on input. Let's see. So if we have array of size n, so we have n elements in the array, what will be the total number of operations here? Let's go. So what is the total number of operations? So here we have one operation to initialize the variable s. Here we have cycle. What number of operations we need to go to the next iteration of the cycle? Let's say we have here, it may be different again, some details. So here we need to increase the value of I, then compare I to n, check if I is less than n, and then go. So it's, let's say, 2 operations per cycle. So we have 2 n operations spent here. Here we have some plus equal. It means we need to load this element from the array, then calculate this sum, and then put this sum into variable s. So let's say we have like 3 operations per cycle. So on each iteration, we spend 3 operations here. So total number of operations we spend here will be 3n. Something like that. And finally, we need 1 operations to output. So the total time complexity of this algorithm will be the function of n. And it will be like 1, 2 plus 5n. n is just, maybe we need to load this from array, then calculate this sum, and then put this sum into variable s back. So we need like about 3 operations. It's not very important, we'll talk about it later. Yeah, so when we calculate the number of operations, we have something like that. So this is some function which explains how the time grows when you increase the size of the input. Now let's take this formula and remove everything which is not important. Let's look. For example, this plus 2 is not important. Why it is not important? Because this 5n is much bigger than this 2. We will talk about master theorem in the end, but not now. This 5n is much bigger than this 2. So this 2 is not very important. Let's remove it. Now, let's look at this 5n. In this 5n, this constant 5 is actually not very important. Why it is not important? Because it actually depends on very different details. So this 5 may be different if we fix another set of operations. So if, let's say, we have operation plus equal in one operation, we will have not 3n but n here. So it will be not 5n but say 3n and so on. So this constant 5 is not the property of the algorithm, it's property of its realization. So if we make this cycle in some different way, we may have different constant here. So this constant is not the property of the algorithm. It's just how good we are in programming. So it is not a property, so we remove it. But this n is important because this n is a property of algorithm. So if you make slightly different cycle and like calculate it in different order and so on, you still will have some function which has this n. You may have different constant here, but this n stands the same. And to describe situations like this, there is a special theory. So it's written like this, it's big O of n. You may see this, so again, if you take part in programming competitions and you read some tutorials, you may be familiar that this sign big O. So what this big O stands for? Big O stands for this following. So it's just the short symbol to describe the following situation. So if one function is big O of another function, what does it actually mean? It means that after some value n0, I will use some quantities here. So it means exists. So there exists some constant n0 and some constant c, such that after point n0, so for all n greater or equal than n0, this function f is no more than c multiplied by function g. Again, this is the formal definition of this big O sign. So whenever we use this big O sign, we actually mean this. So, for example, I don't understand what's going on. Okay, I don't see any questions here again. If you have any questions, just post them into chat. So don't spam too much, but if you have questions, just post it immediately. Let's prove that this function is actually big O of n. Let's do it. So let's do it here. So we want to prove that 2 plus 5n is big O of n. How to prove this? We need to find some constants n0 and c such that this holds. Okay, any guesses? Try to find values of n0 and c for these functions. Again, here, function f is 2 plus 5n, and function g is simply n. And we need to find constant n0 and c such that for big values of n, f of n, like this function, is no more than c multiplied by g of n. Come on, any guesses? So we need to find value n0 and value of c. For what variable? So we have two constants, n0 and c. Five is a good number, but for what constant? C equal to 5 and equal to 1. Let's check. And 1 is equal to 5. Well, let's check. So we need to prove that 2 plus 5n is less or equal than constant c, which is 5, multiplied by function g, which is n. That's obviously not true. So 2 plus 5n is greater than 5n. So this pair of constants just doesn't work. N equal to 5, c equal to 2. Now, if you have c equal to 2, then you have constant 2 here. That's even worse. So now you have 2 plus 5n less than 2n. But if n is big, then this is actually much bigger than this. So again, it's not working. Yeah, well, c equal to 6 is much better. So if c equal to 6, let's see. So if we take c equal to 6, then we have this equation. In this equation, let's just decrease. So let's move it to the right, remove this. We will have something like angle 2. So if we take n0 equal to 2, we will have the true equation. So again, if n is greater or equal than 2, then we have this equation. This 2 plus 5n is less or equal than 6n. So if you take these two constants, you have the correct proof. Or you can, oh yes, you can take 1 and 7. That's all it also works. Yeah. Constants 1 and 7 also works. Okay, now we proved our first time complexity. So time complexity of this algorithm is big O of n. Good. Now let's move to something different. So what I want to talk about. So this big O notation is actually the upper bound of the complexity. So it's not the real value of complexity, but upper bound. For example, let's prove that n is big O of n squared. Let's prove this. No, it's easy. So, for example, let's take n0 equal to 1, c equal to 1. So we have n is less or equal than n squared. That is true if n is greater or equal than 1. So if n is greater or equal than 1, then n is less or equal than n squared. So formally, n is big O of n squared. So this big O notation shows not the real asymptotics, but the upper bound of this asymptotics. So when you prove that your algorithm works in big O of n time, you prove that your algorithm is not slower than big O of n. Sometimes, let's see here. So when you want to prove your algorithm is fast enough, you prove that your algorithm's working time is big O of some function. Sometimes you want to prove that your algorithm is not fast enough. So you want to show that the time complexity is big. For these cases, there is some other notation. Other notation is not big O, but big omega. So sometimes we need to use like this, big omega of b. Big omega is the same thing, but not less or equal, but greater or equal. So it is, again, there exists some constant n0 and c, so for all n up to n's, f of n is greater or equal than c multiplied by j of n. So this big O is upper bound for the complexity, and this big omega is the lower bound of the complexity. For example, let's show for the same function that the time complexity of this algorithm is big omega of n. Again, let's guess some numbers n0. So we need to fix numbers n0 and c such that 2 plus 5n is greater or equal than some constant multiplied by n. Any guess again? That is simple. One and one, good. One and one works. So if you have one here, then you need to prove that 2 plus 5n is greater or equal than n. That's obviously true. Cool. So now we prove that the time complexity is big O of n, and the time complexity is big omega of n. And when you have situation like this, like you have the same upper and lower bound on the complexity, they have a special symbol for this. So when you have these two equations, then you have T of n equal to big theta of n. So that's a special sign which means that you have lower bound asymptotic bounds are the same. Cool. So if you read some special articles about algorithms, then usually when someone invents some new algorithm, they try to not only prove the upper bound, but also prove the lower bound. So the real result of the real article usually is something like that. But in this course, I will almost never use lower bound. I will prove only the upper bound of the complexity, just because to make the course more simple, because it is more important to prove the upper bound. When you prove the upper bound, you show that your algorithm is fast enough. When you prove the lower bound, you show that your algorithm is not fast enough. So it's slow enough. And usually when you design algorithm, you want to prove your algorithm is good. So to prove your algorithm is good, you need only upper bound. Good. So in this course, I will mostly always prove only the upper bound. But in the real world, in most cases, you want to prove both these bounds. Just if you're writing the real article, you want to prove both bounds and get something like this. Good. Now, how to calculate this number of operations for your algorithm? There are different cases. So sometimes it's very simple. For example, if you have like two cycles, you have cycle I from 0 to n minus 1, and then inside you have cycle j. And what is the time complexity? N squared, good. So time complexity of this algorithm is n squared. That's quite trivial because this line is executed exactly n squared time. So we have n squared time executing this line. If you have something more complicated, let's say we have not to n minus 1 but to I minus 1 here. If you have something like this, we can just calculate the number of times we execute this line. this line will be executed. So on the first iteration is executed once, then you have 2 times, and so on. So number of times you execute this line is like 1 plus 2 plus and so on plus n minus 1. N minus n. N. Right? No, n minus 1. Because it is from 0, yeah. From 0. So on the when I equal to 0, you have 0 iterations here. Oh, good. So this sum is actually n multiplied by n minus 1 divided by 2. So this is again it's big O of n squared. So when you have 4 cycles, it's usually simple. So when you in your algorithm you have only 4 cycles. 4 cycles are very easy. It's a little bit more complicated when you have wild cycles, and usually you have some of them. So for example, let's say we have I equal to 0, and while I multiplied by I is less than n, I plus plus. What will be the time complexity here? So in this algorithm, you increase the value of I until I square will be greater or equal than n. Yeah, good. So the number of iterations, so you will end this cycle when I square. So you end the cycle when I square will be greater or equal than n. Means that I will be greater or equal than square root of n. And each time you increase the value of I, so the total time you increment the value of I will be up to square root of n. So complexity of this algorithm will be square root of n. Good. Now, let's make something. Let's make something like this. Let's say we have I equal to 1, and while y less than n multiplied by 2. So we just increase the value of I twice on each iteration until I will be greater or equal than n. What is the time complexity of this algorithm? Good. Here we have a logarithm. Again, we will end this cycle, then 2 in the power of if we make k iterations, let's see. Iterations. I will be equal to 2 in power of k. So the number of iterations will be such that 2 in power of k is greater or equal to n. It means that k will be equal to logarithm of n base 2. So the total number of iterations will be up to logarithm of n. So time complexity will be like this. Good. Now, when you have logarithm in your asymptotics, I will usually not write this base of the logarithm. So I will usually write something like this. That's basically because this constant doesn't affect the asymptotics. So if you put any other base here, it only affects the constant, not the asymptotics. So, for example, let's try it here. So you have something log base a of n is big O of log base b of n for any a and b greater or equal greater than 1. So all logarithms only changed by the constant, so they all grow in the same speed. So when I will write in the future, when I will write some big O of some logarithm, I will just omit this base of the logarithm. Cool. Yeah. Nice timing. So, next. Now, let's talk about recursive algorithms. Some algorithms we'll talk about, even in this lecture, are recursive. So they have some function which calls itself. So let's write something. For example, let's say we have f of n, like in Python, let's say that. Okay. So we have some function, and it do something like this. So let's say if n equal to 0, then just return. And if it is greater than 0, then we will call f of n minus 1. So, what happened if we call f of n here? Now, to calculate the time complexity of the recursive algorithm, we need to calculate the number of times you call the recursive function, and for each call of recursive function, add the time you spend when you make this recursive function. So, now, each call of this recursive function works in constant time. We don't have any cycles here. So this all works in constant time. So beside this all works in constant time. So to calculate the total complexity and the total number of operations, we need to calculate the number of times we call this function. So what will be total time? So when we call f of n, what will happen? We call f of n. It will call f of n minus 1. It will call f of n minus 2. And so on. Until we call f of 0. So the total number of its recursive calls will be n. So we have n recursive calls. And each recursive call costs you constant number of operations. So the total number of operations will be linear. Is it clear enough? So again, if you have any questions, just ask them immediately. Good. Now let's make something more less trivial. If you have, let's say, here, if you have not n minus 1, but let's say n divided by 2. What will be the time? Let's say this is integer division, so you divide it like integers, just without the remainder. Here again, what happened? You call f of n. Now, from f of n, you call f of n over 2. From this, you call f of n over 4, and so on. So until you call f of 0. And when you make integer divisions each time, the total number of divisions you can have until you reach 0 will be up to log n. So this depth of the recursion will be log n. Just add base 2 just for clearness. So again, total number of operations here will be up to log n. Okay. And now finally, let's make something more interesting. Let's add more here. So let's have 2 recursive calls, n over 2 and another n over 2. Now what will happen here? Now it's a little bit more complicated. Now you have not the sequence of recursive calls, but some tree of recursive calls. So you have some main recursive call f of n. From this call you have two independent recursive calls. So you call f of n over 2, and then again call f of n over 2. Now, each of these recursive calls will also make two recursive calls. So from here you have call of n over 4, and again, and here the same. And so on. So here you have another two calls, and here we have two calls. So we have this tree of recursive calls. Let's calculate the total number of recursive calls. How to calculate the total number of recursive calls? We need to calculate number of nodes in this tree. To calculate number of nodes of this tree, we need to know its length. So what is the height of this tree? So what is... What will be the height of this tree? The height of the tree will be the deepest recursive call. So the number of recursive call in every branch of this tree will be up to log n, like before. Yeah. So we make f of n over 2, and over 4, and so on until we reach f of 0 in the end here. So number of calls on each branch of this tree will be log n. And now you want to calculate the number of nodes in the tree of height equal to log n. What is the number of trees? Let's say since h equal to log n. So if you have tree of height h, what will be the total number of elements in this tree? It will be about 2 in the power of log n. So total number of elements here will be 2 in the power of h. Yeah. So this height of the tree is log n, so we need to put this log n here. So total number of elements in this tree will be 2 in the power of log n base 2, which is n. So the time complexity of this algorithm is linear actually. Is it clear enough? So this happens sometimes. So you have some strange recursive function, and when you calculate the total number of recursive calls, you have something similar in there. So you don't ask questions that make me suspicious. You don't understand things. Well, that's the question. Okay, let's if you don't ask any questions, I don't understand if you agree with me or not. So, let's see. If you have tree, so we have some first layer, second layer, third layer, and so on. So, on the first layer you have one node. On the second layer you have two nodes. You have 4 nodes here, 8 nodes here, and so on. So in the last level, you will have 2 power h nodes. Now we need to calculate sum of all these elements. So we need to calculate sum 1 plus 2 plus 4 plus and so on plus 2 in the power of h. This is sum of geometrical progression. So the sum of these powers of 2 will be like 2 in the power h minus 1 minus 1. And this is big O of 2 in the power of h. Two plus 1. So when you have tree of height 2 in the power of h, total number of elements in this tree will be big O of 2 in the power of h. Is it more clear now? Okay, I hope now it's more clear. And now here the height is logarithm base 2. So if you have 2 in the power of logarithm base 2 of n, you will have n. Cool. Cool. Wait, now let's complicate it a little bit more. Let's add like third recursive call. Why not? What happens if we add third recursive call here? Okay, it's your turn. Like, try to do everything the same, but with 3 recursive calls. What will happen? Well, let's see. Yes, again we call f of n, and then we have 3 recursive calls here. Each call is n over 2. Then again we have 3 recursive calls here, 3 recursive calls here, 3 recursive calls, n over 4 here, and so on. Yes, the height of the tree will be the same. The height is log base 2 of n. Cool. So, but yes, the height will be the same, but the number of elements will be different because the branching factor is not 2 but 3. So in the bottom layer we have not 2 in the power of h but 3 in the power of h, because each time we split into 3 branches. So total number of operations here will be 3 in the power of h. And now we need to calculate 3 in power of log base 2. It's not n because this base is different. So this actually will be equal to n in the power log base 2 of 3. So this number is bigger than n but less than n squared. So we have n in some strange power. So what is the log of 3 base 2? It's about 1.7, I think. So it's about n 1 point, maybe less. No. It's about 1.7, not exactly. So it is n in some strange power. So it's not linear, not n squared, but something in the middle. And actually, sometimes it happens. So we will discuss some algorithms which have some strange complexity like this. Height will be log base 2 because each time we split in 2. So we have each time we have n over 2 here. So each time n is decreased twice. Yeah, and that's a good question. I will add this in the practice section. That's nice exercise. Try to solve it. Good. Oh, we spent a whole hour for this. Okay. Now let's move to some real algorithms. So now we will talk about sorting algorithms. That all was like introduction about how to measure the complexity of the algorithm. So time complexity of the algorithm measures something like that. So now let's move to some real algorithms. That's not all. That's not all. We need to discuss one more thing, and we will do it now. Now we will talk about sorting algorithms. What is a sorting algorithm? It's basically the algorithm where you take the array and you return the sorted array. So you have input like array n, a, and output let's say array b, same as s, but sorted. Okay, and the first sorting algorithms I want to talk about is the insertion sort. The insertion sort algorithm works like this. You have some array. and you move from left to right and try to put each element in its correct place. So you move from left to right. On each step you have some sorted prefix. You take the next element, this element, and move it to the left until it reaches its correct position. So you take this element and then try to move it to the left until it finds the correct position of this element. Cool. Let's go. So let's write the code. So we have, let's say we have for I from 0 to n minus 1. Let's say this element is index I. And now we need to move this element to the right or to the left. How we'll do it? Let's say j is the index of the current element we are moving. So first it's I, and now we move it to the left until we reach the left border of, or we reach element which is less than this element. So while j is greater than 0, and we can move it to the left if it is less than element to the left. So if this element is less than element to the left. We will move this element one position to the left. So we swap element aj with element aj minus 1. And decrease j. Looks fine. So this is the basic insertion sort algorithm. Is it clear it's working, or should we prove it? Let's prove this algorithm works. So, how to prove this algorithm works? We will prove it using the following invariant. So, we will prove that after each iteration of this cycle, we have the sorted prefix of the array. So here we have sorted elements from 0 to I. Let's prove this works. If it was sorted on previous iteration, then on the next iteration what happens? We take the next element, move it to the left until, so we have situation like this. So we move it somewhere here, and if this while stops, it means that this aj is greater or equal than the previous one. So it's greater or equal than this. And since we moved it on the previous iteration, it means that we have less here. So we have less or equal here, we have less here, and this part is sorted, this part is sorted. So we have this all elements in sorted order. So these are sorted, these are sorted, this is less or equal, this is less. That's all. It's quite easy. Now let's talk about what is the time complexity of this algorithm. To calculate time complexity, we need to calculate the number of operations this algorithm makes to sort the array. And what is the tricky part? The tricky part is that the number of iterations depends on the input. So for some arrays, this algorithm may work much longer than for other arrays. What is the best case for this algorithm? So, what is the best array for this algorithm? Again to the proof. Let's prove by induction. So let's prove that in the end of this iteration, so after iteration I, you have the sorted prefix of elements from 0 to I. Why is it sorted? Because it was sorted. So it was on the previous iteration we have sorted elements from 0 to I minus 1. So on the next iteration, we take this element, and move it to the left, to some position. We have this part sorted, and here, since we stop moving, we have less or equal here, and we have less here. So the whole is prefix is sorted. So when you move from iteration I minus 1 to iteration I, you have the sort prefix of length I. So in the end, after the last iteration, you have sorted prefix of the whole array. So all the array is sorted. What I want to talk about. The time complexity of this algorithm actually depends on what input you give to him. So for some inputs it's fast, for some inputs it's slow. What is the best case? The best case is when the array is already sorted. So if you have an array like this, what will be the total number of iterations? Let's see. So each time you go into this while, you check that element is less than the previous element, have false here, so you don't go inside this cycle. So on each iteration, you make only constant number of operations and move to the next iteration. So the total time complexity for sorted array will be linear. And what is the worst case? The worst case will be then we have the same array but reversed. Yes, when we have array n minus 1, and so on, 1, then each time we go into this while and make this swap. So we first move this element to the left, this element move twice, this element move 3 times, and so on. Last element will be moved to the first position. So the time complexity here will be n squared. And for the most algorithms we'll talk in this course, things are going like this. So there are some good cases and some bad cases. And to analyze, this is important part, to analyze the time complexity of the algorithm, we will talk only about worst case. So for the most algorithms, for some algorithms it will be different, but most of the time we will talk only about the worst case. So if I don't specify any different, when I talk about time complexity of algorithm, I talk about the worst time complexity. So we find the worst possible input and calculate the time complexity on this worst possible input. Okay, so time complexity of insertion sort is n squared. It means that it's time complexity in the worst case. Okay, good. Yeah. Now let's move to the real algorithm. Finally, let's discuss something interesting. So, finally, let's talk about merge sort. Now we're finally ready to make something not that trivial. Okay, merge sort. Merge sort is another sorting algorithms with time complexity less than n squared. Spoilers. So how does the merge sort work? So the central element of the merge sort algorithm is the merge operation. Merge operation works like this. You have two sorted arrays. Let's make sorted array A, sorted, and B. Let's just to save space, let's move it here. So you're given two sorted arrays. and it outputs the merged version of this array. So we have all elements of this arrays, we merge them into one big sorted array. Let's say C. So let's put some real elements here. So we have some elements, I know 1, 5, and 10 here, and some 2, 4, and 6 here. So in the end we'll have something like 1, 2, 4, 5, 6, and 10. Non-decreasing. It's like small details. If you have non-decreasing or increasing, it doesn't affect anything else. I will say increasing, but it's actually the same if you have non-decreasing also. If you have equal elements, it doesn't affect algorithm as well. So, how to merge two sorted arrays into one sorted array? Let's see. So, you have two sorted arrays. Let's draw it a little bit bigger. And you want to put all these elements into one big array in sorted order. Let's go from left to right. Let's go from left to right. We'll talk about quicksort on next lecture, not next in the lecture, in 2 lectures, I think. So we'll talk about not today. Quicksort is in the plan, but not today. Again, we want to merge these two arrays into one big array. What happens? So let's find the first element we need to put in this merged array. So this leftmost element must be the minimum elements of both arrays. So we have some elements here, some elements here. You need to find the minimal element and put it in the first position. So how can we find the minimal element? Minimal element is either this element or this element. So this is the minimal element in the first array. This is the minimal element in the second array. If you want to find the minimal element in both arrays, you take the minimum of these two elements. Yeah? So let's take minimum of these two elements. It will be 1. And take this 1 and put it on the first position in the result array. So we put 1 here. Now remove this 1. And do the same again. Now, to find the second element, we need to find the minimum of these two elements. So we take minimum of 2 and 5. See that 2 is less. So we take this 2, put it on the second position. Remove this from array. And so on. Each time we have 2 elements in the arrays. One element in the first array, 1 element in the second array. We take the minimal element and move it on the next position in array C. And so on. Let's write the code just. If you have the same elements, you can pick any element. So if you have same elements in left or right, you could take any element. So they will be equal, so you can put them in any order. Let's see. So we'll have 3 variables. So first variable will be the index of the first element of the first array. So it will be I. Here we have index j. It will be the index of the first element in the second array, and we'll have this index k will be the first empty position in array C. Good. Let's say n is the len of A, and m is the len of B. So this is the length of this array. So this is array of size n, and this is array of size m. Now let's initialize our variables. So we have I equal, in the beginning we have I equal to 0, j equal to 0, and k equal to 0. They may have different size. That's fine. If they these two arrays may have different size, it does matter. Okay. You discussed the quicksort. Quicksort we'll discuss not today, but in the future lectures we'll discuss quicksort and how to pick the pivot element and so on. Now, we need to merge these two arrays. So we take, each time we take the minimum of these two elements and put them into array C. Let's say. So there are different ways to implement this. I will implement like this. So while both arrays are now empty, not less n, or j is less than m. So why I have more elements? I will put one element from array to here. Let's say, so when I need to move element from the first array, I need to move element if second array is empty. So if b equal to m, or if first element is less than this element. So, or if I less than n and I is less than bj. Just spend too much space on this on this bar. Go. So if we have something like this, so if we have second array is empty, or if the first element is less than second element, then we move this element from array A to array C. Let's say C k plus plus equal to a I plus plus. Here I use plus plus like in C++. There's no plus plus in Python, but I like how it works when you add element into array, so I will use plus plus in this pseudocode. This code is just combination of all good techniques in different programming languages. Cool. So we move this element to array C and increment k and increment I. Else, we need to move element from array B. So we again we'll do the same. We move element from array B. That's all. Yes, we can. Yes, we don't talk about memory complexity here. Yes, here we need to merge these two arrays. We need to create another big array. This is not exactly optimal way to do it. You can do the same without additional memory, but we will not talk about it today. It's kind of complicated. So we will create another array and just put these elements into different array. Just spend another n memory to create another array. It's not optimal, but fine for today. Where? C equal. I didn't create array C, but I think it's fine. You need to create array C of size n plus m. Somewhere here, let's say C is array of size n plus m. Something like that. Just create the array, initialize it to 0, something like that. C is the array, this array. You need to initialize it somehow, yes. I agree. Good. Now, let's calculate the time complexity of this algorithm. Now it's a little bit more tricky. Again, when you have while cycle, it's usually more tricky to calculate the time complexity. to calculate time complexity, you need to calculate the number of iterations of this cycle. And usually the best way to calculate number of iterations is to make some half invariance. So let's look on some value which increases every time you make another iterations of the cycle. For example, in this cycle, each time, if you look on the value I plus j, and on each iteration, you either increase I or j. So on each iteration, this sum will increase by 1. And in the beginning, you have I plus j equal to 0. In the end, you have I plus j equal to n plus m. And on each iteration, this sum I plus j increased by 1. So the total number of iterations will be equal to n plus m. I believe there is an easier way to prove this, but more intuitive way to prove this is like every time you pick the element from the array and move it. So total number of elements is n plus m. So if you remove one element each time, then total number of iterations will be n plus m. So it's not that difficult actually. Okay, so we can merge two arrays A and B of size n and m in total time n plus m. That's pretty good code actually. You can program it like this. It's actually pretty efficient. Okay, now the b equal m. Where is b equal m? Not b. That's my bad. So j equal m. Okay, my bad. J equal m. Of course. Yes. J, I, J. Yeah, that's fine. Small bug. Okay. Well, actually, thank you for pointing. Good. Now, what we need to do, we need to, using this procedure, make a sorting algorithm. How to create a sorting algorithm when you can merge two sorted arrays? You can do it the following way. We will make the algorithm using the divide and conquer technique. Special name for this technique. Okay, how to sort the array? So you have array. This is merge. This is sort. Sort array A. We have array A, and we need to sort it. How divide and conquer technique works? You have some array, and you need to perform some procedure. You split this array into several parts. In our case, in two parts. So we'll split this array into two halves. Let's half. Let's call them B and C, just for simplicity. So B is the left part of the array, and C is the right part of the array. Now we will call the same recursive function for both halves of the array. So we will call operation sort for array B and operation sort for array C. So we will have two sorted arrays. We'll have sort array B and sort array C. And in the end, we will merge these two arrays into one big array. So we will call this merge procedure and merge these two arrays into one big array. So we'll have one big sorted array. That's the plan. Again, what is the plan? I'll just write the code here. It will be very easy. So you have array A, you split it into two halves. Let's say B is the left half, let's say A from 0 to n divided by 2 minus 1, and C is the right part. So it's A from n divided by 2 to n minus 1. So these two halves. Now we call the same function for these two arrays. And then we merge these two halves into one big array. Oh, my bad. If you make a function like this, it will never end. So if you make recursive function, you need to stop it somehow. Here I always have these recursive calls, so this recursion will never stop. You need to stop the recursion at some point. And here, let's say if fix, small fix, up. Let's say if length of array A is less than 2, then just return A. Now it's fine. So again, how it works? If array A is small, it's one element or it's empty, we just return the same element. It's already sorted. If it has at least two elements, we can split it into two parts. So we split it in the left half and the right half. Then we sort both halves using the same algorithm. Just call this function sort is the same as this function. So we just call the same function here. And then merge these two arrays into one big array. Cool. Looks fine. Yeah, looks fine. Good. And final thing, let's calculate the time complexity. Now, using all we learned today, we need to calculate the total number of operations of all these recursive functions together in this stuff. So, how to calculate the time complexity of this function? Again, this is a recursive function. We already did similar thing. So, we have recursive function, we have two recursive calls. Let's say that T of n is the time complexity of array of size n. So what happened here? Here we have two recursive calls. But each recursive call have array of twice smaller size. So we have two recursive calls, each call spend time t of n over 2. Have t of n over 2 here, t of n over 2 here. And now let's calculate the time complexity of all other lines here. So we need to split array here, and we need to return merge here. So time complexity of all other lines is linear. So we need to spend big O of n time here to calculate this merge. And we need to spend big O of n time here just to make this split. So the total time complexity will be 2 multiplied by n over 2 plus some linear stuff here. So plus, let's say, some c multiplied by n. Good. Yeah, we had almost the same recursive function before, but what different here? Here is this part. So here we have additional linear processing time in each recursive calls. So again, what happened? That's right. So what's happening here? So we have a recursive call of all the array of size n. And then we have two recursive calls of size n over 2. Then we have 4 recursive calls of size n over 4. And so on. But now we need not to calculate the number of recursive calls, but we need to calculate the total number spent in all recursive calls. And in each recursive calls, we spend not the constant time, but linear time. So in the main recursive call, we make these two recursive calls and then spend another n time to calculate this merge. Now we make two recursive calls. In each call, we spend another n over time 2, or n over 2 time, to calculate the merge in each two sections. So we calculate merge here in n over 2 time, calculate merge here in n over time. So we spend n over 2 time here and n over time here. So we need not to calculate the number of nodes here, but to calculate the sum of all elements here. So let's calculate the sum of all numbers in this tree. How to calculate this sum? Easiest way is just to look on this tree and calculate it. So on each level, the sum of all numbers is n. So we spend n time on this level. Here we have n over 2 here and n over 2 here. The sum is n. Here we have 4 recursive calls. Each recursive call makes n over 4 operations. So the total number of operations in all these 4 recursive calls will be n, and so on. So on each layer, we have sum of all these recursive calls will be n. And the total number of these layers will be log n. So the sum of all these layers will be n multiplied by log n. It means the total complexity is n log n. Another if you're more mathematician than I am, so this is like more intuitive approach to calculate the time complexity. You can perform more mathematical approach to calculate the complexity, and you can do it using the mathematical induction. So how to calculate? Let's prove by induction that t of n is less or equal than, we have c here. Let's use another constant. No, let's say it says c n log n. Let's prove that time complexity is no more than c multiplied by n log n. Let's prove it by induction. So suppose it is correct for the smaller n. How to prove it for bigger n? We need to make a transition from small n to bigger n. So we put this n into here. We have t of n. T of n is 2 times t of n over 2. T of n over 2 is, so we have 2 multiplied by this time, so c n over 2 log of n over 2 plus cn. And now just simplify this, so we can get rid of these 2's. Log of n over 2 is n minus 1. So we have c of cn log n minus 1 plus cn. Then you simplify this, you have cn log n minus cn plus cn. So it is c log n. So you can prove it like this, just by induction. You suppose it's working for small n, and then make the proof for the big n. N log n is bigger than n. Yeah, that's correct. Okay. Looks fine. Oh, yeah, it's perfect timing. Yes, I plan to end about this time. So, any more questions? Okay, the final thing I want to talk about is about master theorem, just to mention it. So, the formulas like this are usually happening when you have algorithm which divides the input in some parts and call the recursive function. So there are a lot of algorithms which use the divide and conquer technique, but with some different constants. Let's write it here. Recommend a book. I don't know a good book. There's a Corman book, classical Corman book about algorithms, but not something more. Let's get coding exercises. Yep. We'll talk about coding exercises. I think I'll make a post on code forces and we'll discuss what is the best way to make practice. Good. Final thing. So we have formulas like this in various different algorithms. So when you have algorithm which splits the input into, let's say, B chunks and then make A recursive calls. So you say again, let's say you have algorithm like this. You're given some input of size n. You split it into B parts and make A recursive calls. So you have A recursive calls here. Usually A is bigger than B because when you split the input, you need to make at least one recursive call. But not always, but usually A is bigger than n. Now, in the end, you make some additional operations just to combine all these results, and this costs you. I already have F. Let's rename the function. I want to use F. And in the end, you spend another time just to combine these results into one. So we have some F of n here. Now, how to calculate time complexity of such algorithms? So, what is the time complexity of this algorithm? Let's say T of n. So we have A recursive calls of size n over b. So we have A multiplied by T of n over b plus some F of n. So situations like this happens all the time. So they make a special theorem about situations like this. It's called the master theorem. Master theorem is the theorem which calculates the time complexity of algorithms of this form. Let's go. So let's start from the simple cases. So if oh cool. So if you remove this f of n, so if you say f of n equal to 1, so what will be the time complexity? Again, what will happen? You have some tree which have branch factor equal to a. So each time you have a recursive calls. A. So each time you have a recursive calls, and the height of the tree will be equal to log n base b. Right? So the total number of elements in this tree will be a power log b n, like this. It's equal to n in power log ba. Again, we already discussed this. Like we discussed when you have b equal to 2 and a equal to 3, but it's just generalization of this. So when you have branch factor equal to 2 and you divide input by b, then the height of this tree will be equal to log base b, and total number of recursive calls will be n in the power of log base b of a. And now, what the theorem says? The theorem says that if this function f is much less than this n in the power of plus b, for example, if f of n is big O of, again, it will be a very simplified version of master theorem. We'll just do not try to add more difficulties. Also, let's say if f of n is big O of n in power like here, log base b of a minus epsilon. So it is some polynomial of power less than log of a power or base b. So it is much less than this polynomial. Then the time complexity will be this. Basically what happens, then this number of recursive calls just is much more than the total time you need to spend on this f function. So the most time your algorithm spent is just making these recursive calls. On the other hand, if n is big O of some bigger function, so it's log, let's say plus epsilon. So if this function f is much more than this function, then the time complexity will be the same as function f. It's not exactly the true, but better write this. Yeah, it's more correct. So the time complexity will be the same as the function f. And finally, if the complexity of function f is the same as this, then the total complexity of the algorithm will be like here. It will be multiplied by a logarithm. So this is basically how the master theorem works. So if this function f is slower than these recursive calls, then the total complexity will be the same as this function f. If it is faster than this recursive calls, then the complexity will be the same as this recursive calls without fast function. If it is the same as this recursive calls, then you will add logarithm factor here. That's basically all. Any more questions? No? No more questions? How to... let's use master theorem to calculate time complexity of the merge sort algorithm. So in our case, what happens? So you have function like this with a equal to 2 and b equal to 2. So we have a equal to 2, b equal to 2. So we have n in power of logarithm of a base b. So logarithm of a base b equal to 1, because it's logarithm of 2 base 2. So we have this third case, and this function f is c multiplied by n. And this function f is big O of n. So we have this third case, n the power of 1. Let's make it simple. So we have this third case. So in the third case, the time complexity will be n in the power of log, this n the power of 1 multiplied by log. So time complexity will be n in the power of 1 multiplied by log n. Should we use theta? Yes, you can use theta here. Like I said in the beginning of the lecture, I will most usually use big O instead of big theta, just because I'm lazy and I don't want to prove lower bounds. But yes, in the regional master theorem, you can use theta here in all places. It will be even more accurate. That's correct. That's correct. Okay, thank you for watching. So that's all for today. See you next week. I will make a special post about this course on the code forces, and we'll discuss the best format for the practice problems. Okay, so see you next week.